Hi friends, right now we will be talking about electronic configuration of elements in terms of across a period as well as the electronic configuration of elements. Then after that we will be talking about in a particular group in the periodic table. Now let me be very clear at this point that you guys need to actually know the last part of the chapter called as atomic structure to understand what we are going to do right now. What we are going to do right now will look like German or French to you. It is rocket science. If in case you don't understand the last part of the chapter of atomic structure related to quantum numbers. So you guys need to understand what is the meaning of principal quantum number, what is the meaning of azimuthal quantum number, what is the meaning of magnetic quantum number, and finally what is the meaning of spin quantum number to understand what I am teaching right now. So if in case you don't know the last part of atomic structure, then you can stop at this part because you won't be understanding head nor tail of what I'm going to explain to you. So this part is only for those guys who have understood, who knows all the different types of quantum numbers and who knows the difference between the term orbital and subshells, and who knows what is the meaning of principal quantum numbers as well as the other quantum numbers. So with the assuming that you have got the knowledge about those stuff, let us start with writing down the electronic configurations of the elements in different in different periods. So in the case of the first period, let us write down the elements. In the case of the first period, we know that this is the first period, right? Let us write down this as the first period. Let us write down this as the first period. So let this be the first period of the periodic table, right? Let this be the second period of the periodic table. Let this be the third. Let this be the fourth. Let this be the fifth. Let this be the sixth period. And finally, let this be the seventh period of the periodic table. So here, once we have written down all the periods of the periodic table, let us quickly write down the electronic configuration that will be involved in all of them. So here we will be having the electronic configurations written as follows. In the first element, we know in the first period that we will be starting with hydrogen, right? Now, hydrogen in the periodic table is occupies a very interesting position, as we have seen in the long form of the periodic table, because hydrogen acts like hydrogen has a tendency of both giving out the one electron which it has. If in case it does, it will occupy the first position in the periodic table, just above lithium, because it will be coming under the category of alkali metals. However, the same hydrogen can also be involved in accepting one electron from outside, from an element which is less electropositive, which is less electronegative than it, sorry. So therefore, if in case we have hydrogen in such a situation, in that case hydrogen, instead of being placed here, it should be placed in group 17 belonging to halogens. So because hydrogen has this peculiar situation of being capable of having diverse properties, like it can act as alkali metal, which is the one extreme end of the chemical chart. It means that it is highly electropositive, and it can also occupy halogens, which is an extreme end of the chemical characteristics, in which it has high tendency of accepting an electron and which is highly electronegative. So therefore, because it can show both the characteristics, that this one element can show different characteristics depending upon the different situation which it encounters in a chemical reaction. That is the reason why we ensure that hydrogen doesn't occupy this position, but it occupies a separate position in the periodic table. So we write down hydrogen as a separate part in the periodic table. We do not include it here. But just as of now, because we are studying the electronic configurations, hence we will be writing down hydrogen temporarily here, because electron configuration wise it shows the characteristics of alkali metals. because it will have, as I'm going to show you, it will have an electronic configuration of 1s1 in short as ns1, because this will show the characteristic of 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. In short, it will be ns1. So here, let us consider the situation of hydrogen. So if in case we consider hydrogen here as the first element, the electronic configuration of hydrogen here will be given as follows. Let us, as of now, we are not going to write down elements. We are going to write down only the electronic configurations. So you've got to concentrate, okay? Because here we can't write down, we don't have enough space to write down the electronic configuration as well as the name of the element, both of them, and it will not be necessary. The name of element is not necessary because you can easily look at it in the periodic table, right? So it's of no use mentioning both of them here, and it will be time consuming also. So I'll be saving time in just writing down the electronic configuration because that's exactly what we are going to study here, right? That's our priority here. So here, in the case of the first element, let us consider in the case of hydrogen, we will be having the electronic configuration as 1s1, which basically means that the each period, it is basically meant for different principal quantum numbers. So when we are talking about the first period, it means that the filling of the first principal quantum number. The second period, when we are talking about, it means all the elements that we'll be having in the second period will be in different stages of the filling of the principal quantum number, which is equal to 2. Here there will be a filling of principal quantum number which is equal to 3, that is the third shell. Filling of the fourth shell, fifth shell, sixth shell, seventh shell. Again, each shell basically means the filling up of that principal quantum number. So here there will be a filling up of principal quantum number which is equal to 7. Again, the contrast with in the first period, we know that there will be only 2 elements which will be involved, right? So here we start with hydrogen, and then we will be here finishing with the noble gas element, which will be helium here. So here we will be starting with hydrogen, and here we will be finishing with helium. In the case of helium, we know that in the case of helium, the first shell, in the first shell, there will be S subshell in which there will be total 2 electrons which will exist in the case of helium. So this will be the electronic configurations of the 2 elements which are present in the first shell of the periodic table. In the next shell, my dear friends, we know that it starts with lithium. If in case if in case you want, just keep the periodic table just beside you when I'm writing down the electronic configuration, so that you can relate to each element if in case you want to know the name of the element while we writing down the electronic configurations. See, in the beginning part, I'm explaining to you each and every part of the electronic configuration that I'm writing down. After a certain point, when it will become very obvious, I'll be quickly writing down the electronic configuration of the remaining elements. In total, we are going to write down the outer electronic configuration of 118 elements. When I'm talking about outer electronic configuration, it means that when we have an atomic number as it increases, we are not going to write down the electronic configuration of the inner elements. We will be writing down the electronic configuration only of the outermost electrons which have been put into that. We first of all know how the different blocks are defined, right? As I have told you before, the different blocks are defined on the basis of the last electron in which subshell it is put. If in case we consider for example, S block elements. So this S block element is the element wherein the last electron, it enters the S subshell. So on the basis of that, the blocks are defined. However, there is another anomaly in the modern periodic table, as we can see in front of us, wherein we have helium, wherein in the case of helium, even though the last electron enters the S subshell, we will be, it is not put under the category of S block elements, because S block elements will be this element and this element. These starting two groups will be comprising of the S block element, right? So actually helium should be placed here, but because it is a noble gas, it has to be placed under the category of noble gases, because as I have told you, and as Mendeleev had in his wisdom had realized long before, that the main priority when we are talking about a periodic table, the main priority number 1, which cannot be ignored, even if case the other rules are broken, is that all the elements having similar properties should be present in the same group. So because of that priority, helium has been kept in the last group, which is the special group meant for noble gas or inert gas elements, because they do not react with any other element. Or they have they have least tendency of reacting with any other elements. It's not that they don't react at all. However, actually in terms, technically speaking, in terms of electronic configuration, as you guys realize, this actually should have been here, right? But just to ensure that all the noble gases are present in one group, we keep it here. So this is another anomaly or a drawback of the modern periodic table as we have considered. So even hydrogen was one of the drawbacks of the modern periodic table. So without wasting any more time, let us quickly write down the electronic configurations of the remaining elements. So once you have understood this, we'll be going a bit fast. In the case of the second period of the periodic table, we have the element of lithium. In the case of lithium, in the second shell, we have S subshell wherein one electron is put. So after lithium, we will be having beryllium, right? In the case of beryllium, in the second shell, S subshell, the second electron will be inserted into it. In a similar way, after we have beryllium, we will be starting with boron. In the case of boron, the next electron will be filled in the P subshell. So if in case we talk about the P subshell, we will be having a situation wherein we will be having these last 5 elements. This is 1, 2, 3, 4, 5, 6. So when I say 5 elements, except the noble gases. So if in case we include the noble gas, it is total 6 elements. So we will be having group numbers from 13 to 18, which will be filled here. So let us now try to fill the group number 13. So in the case of group number 13, we will be having in the second shell, the P subshell, there will be 1 electron. Now you will be asking me, sir, what about these 2s2 which has already been filled? Again, realize what I told you in the beginning, my dear friends, that here we are only interested in writing down the electronic configuration of the last subshell in which the electron is being put. Obviously, if in case you write down the complete electronic configuration, the complete electronic configuration of this will be obviously 2s2 and then 2p1. Obviously, even before 2s2, there will be 1s2. So there will be 1s2, then 2s2, and then 2p1. This is 1s2, that is the first shell has been finished. 2s2, that is the in the second shell, there will be 2 types of subshell. That is, there will be S subshell and there will be P subshell. S subshell has been finished, and right now we are in the position of filling up the P subshell. And due to which the last electron, because it is present in the P subshell, and that is the reason why that element is coming in the P block. And this will be the outer electronic configuration in the case of boron. Finally, after boron, we will be going into filling the outer electronic configuration of carbon. Carbon, the outer electronic configuration will be 2p2. Again, in the case of after carbon, we will be getting nitrogen, so it will be 2p3. Here, after nitrogen, we will be getting oxygen, wherein it will be 2p4. After oxygen, we will be having fluorine, which will be 2p5, which basically means that there will be 5 electrons which is present in the P subshell of the second shell, right? So again, this is the outer electronic configuration. Finally, in the case of neon, we will be having a total of 10 electrons, out of which 2 electrons are present in the S subshell of the first shell. 2 electrons are present in the S subshell of the second shell. And then finally, there will be 6 electrons, 2p6, which will be present in the P subshell of the second shell. So therefore, here we will be having 2p6. So this will be how we will be writing down the electronic configuration of the second period. In the case of the third period, it will be very similar to the electronic configuration as we have written down in the second period. The only difference, my dear friends, will be wherein instead of writing down 2, we will be writing down the principal counter number as 3. That's all. So here again it will be 3s1, this will be 3s2. Again, in this case, if we continue writing down, so therefore here the electronic configuration will be 3p1. Again, this will be 3p2. This will be 3p3. This will be 3p4. This will be 3p5, and finally we'll be having 3p6. This will be if in case you want to correlate with the periodic table, this will be here we will be having the element which is sodium. This will be magnesium, this will be aluminum, this will be silicon. Then after silicon, we'll be having phosphorus, then sulfur, then chlorine, and then argon. So these are the outer electronic configurations of all these elements. In a similar way, my dear friends, if in case we want, we can write down the electronic configurations of all the remaining elements which are present in these different periods. So here it will be instead of 3s1, 3s2, this will be obviously 4s1 and this will be 4s2. This will be 5s1 and then 5s2, right? This will be 5s1 and this will be 5s2. This will be 6s1 and this will be 6s2. This will be 7s1 and this will be 7s2. Okay? Once we write down the electronic configuration, again in a similar way, we can write down the electronic configuration of all these elements. The only difference will be, again, all of them will remain P1, P2, P3, P4, P5, P6. Again, here also we will be having the same thing, P1, P2, P3, P4, P5, P6. That part will remain the same. The only difference will be that here we will be having 4, here we will be having 5. Here also in the case of the 6th period, here also we will be having P1, P2, P3, P4, P5, P6. In the case of the 7th period also we will be having again P1, P2, P3, P4, P5, P6. That will be the common factor for all of them. The only difference will be the principal quantum number, wherein this will be 6 and this will be 7. So once we understand that, let us now try to understand the other blocks which are present. So right now, as we have already spoken about the S blocks, this will obviously be the electronic configuration of the S block of the periodic table. So this, as I'm trying to show you here, is a type of building which will be relevant for the S block of the periodic table. So I'm trying not to take up the space for the third group here. So I'm trying to move this line closer here, right? So this will be the S block of the periodic table. Once we are finished with the S block, let's write it down. This will be the S block. Once you finish with the S block, let us also point out the P block. So this will also be the P block of the periodic table. Let us show it. Okay. So finally, this will be the P block. So in this case, we now show the P block of the periodic table. So in the case of P block, you guys now know very well that here we will be having this as the P block. Finally, once we know that this is the P block, let's show it here. This was in terms of the electronic configurations. Let us, in the case of the third period, we will be now actually coming into the D block elements when starting with the fourth period of the periodic table after the third period finishes. So after the third period finishes at the 3s2, 3p6. After it finishes, we will be starting with the fourth period, which is 4s1 and then 4s2. However, after 4s2, we will not be going to 4p6 because, as we have already seen, the number of elements in the periodic table. We know that each of the periods, they will contain the number of electrons which are present in the specific shell of the periodic table, right? So therefore, if in case we know the number of electrons which are present in different shells of the periodic table with the simple formula which is 2n square, you guys must be knowing this, right? So if in case we apply the formula for 2n square, let us look at how many number of electrons and how many number of hence the number of elements that we get in each period, because each element represents to each number of electron which is added. For example, if in case we consider here the element of aluminium, then aluminium will have 3p1. Then if in case we add one more electron to it, then we'll be getting silicon. So as you can see, addition of each electron here will be adding one extra element in the periodic table. So here the number of electrons which are possible in that particular shell will be corresponding to the number of elements which will be present in that particular period. In the fourth period, as you can see, it will be coming into the fourth period in the form of d block elements. So this will be the d block element starting from here to here. This will be the D series, and in the case of the D series, the elements here that will be starting will be from 3d1, and this is how we are going to compensate for the 10 electrons which are still remaining here. So here we'll be starting with 3d1 in the case of group number 3. Again, in the case of group number 4, we'll be having 3d2. In group number 5, we'll be having 3d3, then 3d4, then 3d5, and then finally we will be having 3d6, then 3d7, 3d8, 3d9, and finally we will be having 3d10. So this is how we have total of 10 elements which will be present here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10 elements which are present here are actually a part of the third shell, and therefore the principal quantum number which is given here is 3. So this is the first series which we form in the d block elements, and this is basically called as 3d series. So therefore, if in case we consider the fourth period, we will be having the atomic numbers which will be starting from 19 here. This will be 20, right? There will be total of 2 elements here which will be present, right? So therefore, this will be 90, this will be 20. Again, the first series of the D block will be starting with element with atomic number 21, right? So this will be 21, this will be 22, 23, 24, 25, 26, 27, 28, 29, and finally 30. So therefore, the first series of D block, which is the 3D series, will be starting with atomic number 21 and finishing with atomic number 30. Again, here in the case of P block, if in case we look at the atomic numbers, the atomic number here will be starting with 31, and it will be 32, 33, 34, 35, 36, and it will be finishing with 36. Then, if in case, then we start with the fifth period. In the case of fifth period, the atomic number starts with 37, right? Because we finish with 36 with the fourth period. So this will be 37, this will be 38. Again, in the case of the 4D series, which is the second series that we considered in D block, so which will be starting with atomic number 39, and it will be finishing with, let us see which atomic number, because once we complete total of 10 elements. So this will be from 39 to 48. So this will be 39, 40, then 41, 42, 43, 44, 45, 46, 47, then 48. So we have the last element here in this D series, 4D series, will be having an atomic number of 48. Here the atomic number will be 49 in the first element of P block of the fifth row. So therefore, this will be after 49, this will be 50. This element will have atomic number 50, 51, 52, 53, 54. So this finishes with atomic number 54. That is, right now we need to start with the atomic numbers of the element of the sixth period. So therefore, after 54, here we can start with 55. Here we'll be getting 56 atomic number. So here the atomic number of lanthanum will be 57. However, the atomic number of the element coming after lanthanum, which is hafnium, will not be equal to 58, because we will be starting with the element which is cerium from the 4F series. See, try to get the point. After lanthanum, which is present here, we will be starting with the 4F series, and that is the reason why the entire 4F series is called as lanthanides, because the elements of this 4F series start after lanthanum, right? So therefore, after lanthanum, we will be going from here to the 4F series. If in case we show it, we will be going to the 4F series. After we complete 4F series, we will be then be coming back to the next element which is present, which is hafnium. So therefore, after 57, here will be for cerium, the atomic number will be 58. Similarly, this will be 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71. So here we will be having total number of elements equal to 14. So therefore, starting from 58, we will be having total 14 electrons which will be distributed in the F subshell. So after that, after 71, we will be getting the atomic number of hafnium as 72 instead of 58. So that's one thing which you guys need to remember, right? So after 72, here we'll be having atomic number 73, 74, 75, 76, 77, 78, 79, 80. So this will be atomic number 80. The last element of this is 3D series, this is 4D series, this is 5D series. So the last element of 5D series will be having an atomic number equal to 80. In a similar way, my dear friends, we will be having here the first element of 6p series will be having an atomic number of 81. So this will be 82, 83, 84, 85, 86. Again, the atomic number 86 will be the last for the last element, which is a noble gas of the p block, the 6p series. After 6p series, we will be again be starting with the 7s series. So this will be after 86, this will be 87, this will be 88. After 88, again we will be starting with actinium, which is having an atomic number equal to 89. As I have already told you, after atomic number 89, we will be having a situation wherein we will be the electronic configuration after 89 will not be continuing in the D series, it will be continuing in F series. So after 89, we will have to consider the 5F series. After 5F series is completed, then we will have to come back here to this second element. To the second element after actinium. So this will be this element, right? So let us write down quickly the atomic numbers so that we understand the entire periodic table in whole. And in this specific case, after 88, we will be having 89 as actinium. This will be 90, atomic number starting with 90. So after, if in case we start with 90, the last element will be having atomic number 103. Let us quickly do so. This is 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103. So therefore, we have total 103 atomic number for the last element of the F block. After 103, here we will be coming with 104. So this, if this is 104, this will be 105, 106, 107, 108, 109, 110, 111, 112. So this last element here will be having an atomic number of 112. Again, here starting with 113 will be the last p series, that is the 7p series. Again, there will be 6 elements to it. So if this is 113, this will be 114, 115, 116, 117, 118. So this is how, my dear friends, we have got total 118 elements in the periodic table. If in case we consider all the different blocks, the S block elements, the D block elements, the P block elements, as well as the F block elements. So this is how, as I told you in the beginning stage itself, if in case you point out the atomic number of any element here in the periodic table, or if in case you give me the atomic number, I can exactly point out where that element will be present in the periodic table. Say for example, if in case you point out atomic number randomly, like say for example 99, in that case we can understand that atomic number 99 will be present at a particular part, that is, it will be present here in the F series. Because after 89, we have got 90 here. So this will be 91, 92, 93, 94, 95, 96, 97, 98, 99. So this 4F10, below that, this element will be having an atomic number of 99. So this is how, just if in case you tell me the atomic number, I can exactly point out where it is present in the periodic table. Or the other way around, if in case you show me any position in the periodic table, I can tell you exactly what will be the atomic number of that element. If in case you show me, say for example, this position in the periodic table, I can tell you the atomic number of that element, because it will be very simple. If in case we start here with 72, this will be 73, 74, 75, 76, 77, and this will be 78. So this element in the periodic table, whose position you had shown me, would be having an atomic number of 78. In a similar way, we can go on as much as you want. We can find out if in case you have got the atomic number, we can show the position of the periodic table. If in case you have shown the position in the periodic table, you can easily find out the atomic number using the method that I have shown you. So as you can see, my dear friends, we have different blocks which are being filled. So we have here the S block which is being filled. Here in between we have D block which is filled. Here we have got the P block which is filled. Here we have got the F block which is filled. However, once we finish everything, let us write down at least one elements complete electronic configuration. Let us see how do we do so. Let us write down the electronic configuration of the most difficult element which we can consider here. Let us consider that element obviously as equal to element number 118, right? So for element with atomic number 118, that is un octium, let us write down its electronic configuration quickly. So in the case of un octium, we will be having its short form as UUO, right? So let us write down its electronic configuration. Its electronic configuration, if in case we write down, it will start with hydrogen, it will be finishing with helium. So it will be finishing with the first subshell of the first principal quantum number, which is equal to 1. So hence we will be having here 1s2, which is finished. After 1s2, which is finished, we will be having the second subshell, which is present after 1s2, which is 2s2, which is finished. So after 2s2, we have to complete 2p6. After 2p6, we again have to complete 3s2. After completing 3s2, we have got to complete 3p6. Then we have got to complete 4s2. Then we have got to complete 3d series, which is 3d10. Then we have got to complete the p series, which is 4p series. That is 4p6. After completing 4p6, we have got to complete 5s2. Then we have got to complete 4d10. So I hope so, my dear friends, you are able to understand what I am doing here. I am completing one entire period, that is from left to right. Once we have finished in the extreme right after P series, we again come back to S series of the next period. So this is a very simple rule which you are following and with which you are writing down the electronic configuration of any element in the periodic table. As of now, we are considering the most difficult element, that is the last element having atomic number 118 in the periodic table. Let us see how we complete this. After completing 4d10, we will be completing 5p6, right? After completing 5p6, we will be completing 6s2. Then we will be completing 5d10. However, before completing 5d10, we have got to complete 4f. So therefore, we have to complete 4f14. After completing 4f14, we have got to complete 5d10. Right? After completing 5d10, we have got to complete 6p6, because 6 electrons can be accommodated in p subshell. We know it very well, right? 10 electrons can be accommodated in d subshell. 14 electrons can be accommodated in f subshell, and 2 electrons can be accommodated in s subshell. So therefore, after 6p6, that is here, we will be again starting with 7s. So here we will be again having 7s2. After 7s2, we will be again have to complete 5f14. After 5f14, we need to again come back to D series. So therefore, we will be having 6d10, wherein the 6d series is completed. And after that, we have got to complete the last subshell which is present here, which will be 7p subshell. So therefore, after that, we will be having 7p6. So what you can do, my dear friends, is that just to be sure, alternatively, what you can do is that you can add the numbers here and add the number of electrons which are present in each subshell, and in total you will be getting again 118. This will be the last method of cross checking if in case the total number of electrons is equal to 118, or if in case you have an element equal to 118, atomic number equal to 118. So what you need to do is simply, like say for example, this number is 2, which is present. The number which is present at the top, this represents the number of electrons which are present. So here the number of electron is 2, here the number of electron is 2, here the number of electron is 6, here the number of electron is 2. That way, you just need to count in this way, the total of it will be equal to 118. That is equal to 2 plus 2 plus 6 plus 2 plus 6 plus 2 plus 10 plus 6 plus 2 plus 10 plus 2 plus 14 plus 10 plus 6 plus 2 plus 14 plus 10 plus 6. If in case you do the total of all of them, the answer will be coming equal to 118. So this is how, my dear friends, we write down the electronic configuration of all the elements. Obviously, if in case you have got to write down the electronic configuration of an element, which is say for example here, the electronic configuration will be finishing here. That is a outer we need to complete up till here. Then here it will be 5s1, 5s2, and say for example, if in case we are considering the element here, in that case this will be 4d1, 4d2, 4d3, 4d4. The outer electronic configuration will be 5s2, 4d4. It will be finishing early. Right now we have finished, we have considered the last element, hence we had to cover the entire length of the periodic table. So this was the element that we had considered was the most difficult element to write down the electronic configurations for. So my dear friends, this was the electronic configurations of all the elements in the periodic table when we are considering the arrangement of elements across a period. So if in case you want to consider the electronic configuration of elements in a particular group, let us see. So here the part B will be the considering the electronic configurations of elements not across the period but from up to down in a group. From up to down in a group. If in case we consider from up to down in a group, here we will be having a general electronic configuration for the first group of the periodic table. The general electronic configuration can be written in terms of for S block elements. In the case of S block elements, the general electronic configuration here will be written in terms of NS1 because the number of the period we don't know, right? The number of this principal shell we don't know, principal quantum number. Hence we write it down as n because it can be either 1, it can be 2, it can be 3 depending upon which period the element is present in the periodic table, right? Therefore, in the second group, it will be in terms of NS2. So therefore, it will be NS1 to 2. That will be the electronic configuration of the S block. In the case of D block, the electronic configuration can be given as before D block, my dear friends, we have got to complete the S block also, right? So it will be NS2. After the S block is complete, we start with D block. So therefore, in the case of D block, it will be NS2, then N minus 1, D 1 to 10. I hope so you understand this electronic configuration, how we have written it down, right? Because in the case of D block, we need to understand that first of all, this S block has to be finished. After, say for example, 4s2 is finished. Let us consider this n as equal to 4. 4s2 is finished. After that, the number of the shell number is 1 less than 4, right? And that is the reason why it is 4 minus 1, which is equal to 3. And that is the reason why when we consider 3, then we have total 10 electrons which can be accommodated here, and hence it is 1 to 10. This is a simple way of understanding if in case we give a numerical value to n. In a similar way, let us write down the electronic configuration which will be applicable in the case of say p block elements. P block elements will be more simpler, right? So in the case of p block elements, let's write it down. So in the case of p block elements, we will be considering it the electronic configuration as NS2 and then NP6. Again, in the case of p block elements, it will be anywhere from 1 to 6 because the first element will be starting with atom with 1 electron in the p subshell and will be finishing with 6 electrons in the p subshell. Finally, let's write down what happens in the case of F block elements. In the case of F block elements, the general electronic configuration can be written as, let us consider this series, the 6th period. In the 6th period, we will be having 6s2 which is completed. Let us consider ns2. Then we have 1 electron which has been put in the D block. So therefore, we will be having n minus 1 D, which is 1. 1 electron is present here, hence we are representing as 1. And after that, we will have to start writing down the F block. In the case of F block, the number, as you can see, will be 2 less than the number of the S block of the S series. Hence, if it is n here for S, here in the case of F, it will be 2 less than that. Hence, it will be n minus 2. And then here will be F total 1 to 14. So this will be the general electronic configuration of S block elements. This will be general electronic configuration of P block elements. So this is how we give the general electronic configuration of all the different blocks. Now, as you can understand here in the first group in the periodic table, the general electronic configuration will be NS1. This will be NS2. In this case, in the case of first element of the D block, it will be ns2, then that is n minus 1 d1 for this. Here it will for the second element it will be the same. Only difference will be that here it will be d2, which will be ns2 n minus 1 d2. Again this will be ns2 n minus 1 d3. So again this will be d4, d5, d6. That way it will be finishing with d10. If in case we start with P, again we will be having simply written it down as NP1 to 6, which is basically we can write down say for example in the case of aluminium as equal to NS2 and NP1. That will be the electronic configuration of aluminium. Here in the case of P, as we can see the number, the shell number in the case of S and in the case of P are equal. So that is something which you need to note and keep in your mind so that you don't make any mistake. Only in the case of D, it will be one less. The shell number will be one less than S. In the case of F, the shell number will be two less than in the case of S. So this is how we consider the electronic configuration in a similar way, my dear friends. We can also write down, say for example, if in case we consider one particular group, then we can consider that of say a very important group called as halogens, which will be occupying the 17th group of the periodic table. And in that situation, let us write down the electronic configuration which will be possible. In this case, we will be having the electronic configuration of this first halogen as which is fluorine as 2s2 2p5. This will be 3s2 3p5. This will be 4s2 4p5, 5s2 5p5, 6s2 6p5. Then again this will be 7s2 7p5. This will be the outer electronic configuration of all the halogens which are present. Again, if in case you want to write down the entire electronic configuration, then I have shown you the method of how to write down the entire electronic configuration here. You just need to go from left to right in the periodic table. Once you finish a particular period in the periodic table, you need to start with the first element of the next period and again move from left to right in the periodic table to write down the electronic configuration. This method which I have shown you is not explained in any textbook, in any notes, and hence it becomes very much more important that you have understood this. If in case you have found a little problem understanding this, just rewind this video, watch this video again from the different parts that you couldn't understand in one attempt. The only difference is that some students might understand in one viewing of the video, some other students might require 5 viewing, 10 viewing of the same video. Only thing is that if in case you have concentrated properly while understanding this, there is 101% surety that you guys will understand. Right now in this specific video, we are going to calculate the total number of elements which are present in each of the period of the periodic table. So let us quickly draw the general blocks which are present in the periodic table. Now we guys know that we have a block, the first block of the periodic table. It basically contains 2 elements in each specific period. So I'm basically talking about the S block. So in this S block, we know that its capacity, maximum capacity, is for filling of 2 electrons in S subshell, and that corresponds to S block. So in the case of S block, we will be having 2 elements in each of the period in general in the case of S block. However, in the case of after S block, we have the P block. However, in the case of P block, we know that it starts from the 4th period onwards, and that's why let us quickly write down. In the case of D block, we have a total amount of 10 electrons which can be filled in the D subshell, and that is the reason why in each of the D series we will be having total 10 elements which will be present in it. And after that, let us quickly then go to the P block elements. We know guys that in the case of P block elements, we will be basically be having 6 elements per period in the P block elements, because we have 6 electrons maximum which can be accommodated in the P subshell. So that is the reason why, my dear friends, you surely understand that in each of the period that we will be having, we can have 6 elements corresponding to, means wherein each element will be corresponding to the addition of 1 electron in the P subshell. So with this, we now can also consider the last type of block in the periodic table that we have drawn. In that block here, will be basically the F block elements. Now we know that in the case of F block, we have total number of 14 electrons that can be added in the F subshell. Therefore, each addition of each electron corresponds to the addition or the next element that will be here. So that is the reason why, my dear friends, here we have a situation wherein we will be having 2 electrons in the case of H subshell, 10 electrons in the case of D subshell, 6 electrons in the case of P, and 14 electrons in the case of F subshell. So let us now quickly look at what happens if we draw the different periods of the periodic table. So here we have the different periods. So this is basically the first period of the periodic table. So this will be the second period, this will be the third period. In a similar way, this will be the fourth period, this will be the fifth period, this will be the sixth period, and finally here we'll be having this as the seventh period. Okay, so in the case, let us now look at what will happen in the case of each of the 7 periods. What will be the total number of elements that we will be having? So here we know that in the case of the first period, we will basically be having a total number of elements which will be equal to one element in the S block, that is hydrogen, right? We know that hydrogen is the first element in the S block. So it will be coming under the group of alkali metals, and there will be no element here in the alkaline earth metal part. And that is the reason why after hydrogen, we will be directly coming to the noble gas, which is helium. And that is the reason why, as you can see here, we will have a total number of elements here, which is equal to 2. So let us write down the total number of elements which is possible here. The number of elements, right? So here let us write down the total number of elements which is possible here as equal to 2 in the case of the first period. In the case of the second period, we have both the elements here in the S block. So here we have got 2 elements in the S block, and in the case of D block, it has not yet been started. D block will start from here onwards, right? So therefore, in the second period, we have 2 elements from the S block, and then we have got 6 elements corresponding in the case of the second period. So therefore, in total, we have in the second period, total number of elements is equal to 2 plus 6, which is equal to 8. In the case of third period also, we will be having total number of elements as 2 plus 6, which is equal to 8. Next, we have the fourth period, wherein we will be having a situation wherein we have 2 elements in the S block. We will be having 10 elements in the D block, because from the fourth period onwards, D block starts. And after that, we will be having 6 further elements in the P block. So therefore, we have a total number of 2 plus 10 plus 6, which is equal to 18 elements in the fourth period. In the fifth period, we will be having again a total of 2 plus 10 plus 6 elements, that is equal to a total of 18 elements, because here we have basically in the case of this D block, here we will be having 3D series, here we will be having 4D series. So there are 10 elements in 3D series, 10 elements in 4D series. So again, in the case of sixth period, we will have again the 2 elements in S block. We will be having again 10 elements in the P block. How 10 elements? Because again here we will be having 5d10 electronic configuration, and after that we will be having a total of 2 plus 10 plus 6 again, which is equal to 18 number of elements. However, in the case of the sixth period, we also have the 4F series, which will be starting with it. So here we will be in the case of D block itself, we will be having 4F series. So in the case of 4F series, we will be having 14 elements. So therefore here 18 elements plus this 14 elements. In total, we will be having 32 elements in the periodic table. In the sixth period, in the case of seventh period, again here we will be having 2 elements in the S block. We will be having again 14 elements in the F block again, because here we will be having 5F 14 electronic configuration. In the case of D block, we will be having again here this will be the 6D series. So this will be 6d10, 10 electrons in the D subshell or in the D block, and then finally 6 elements in the P block. So here again we have 2 plus 14 plus 10 plus 6 equal to 32 elements. So if in case you add all these elements together, let us see how much is the value that we are getting in this specific case. So here we have 8 plus 2, which is 10, plus 8, which is equal to 18. So 18 into 3 is 54, right? So 54 plus 64. So basically if we have 54 plus 64, so we have 8 here and we have 11 here. So in total we have got 118 elements in the periodic table when we are talking about starting from hydrogen till the last element here in the periodic table, that is we have un octium. You guys know about it, right? Un octium, which is atomic number 118. So we have total number of elements equal to 118 in the periodic table. If in case we consider the number of elements in each period as we have shown here, if in case we simply add them up, we get the value of 118. So this was, my dear friends, everything to do about the number of electrons which are present in each period. Now there is one question which will occur to you sooner or later when we are talking in terms of periodic table, because in the when we were forming the periodic table, it was told to you that each period in the periodic table, it corresponds to different shell which are present in the various atoms. So we know that the number of electrons which are given in the different shells of an atom, they are given by the formula that is 2n square, right? So let us now compare the number of elements in each of the period that we have with the value of 2n square, that is the value of the total number of maximum electrons that can be accommodated in each shell of any atom. So here what we have here is the value, the number of electron in each shell. And when we are talking about total number of electrons, we are talking about the maximum number of electrons which is possible in each shell. And we know that this is given by a simple formula, that is 2 into n square. So we just simply need to apply this formula to get to the final answer. So here, as we can see, here we have maximum number of electron in the first shell as equal to 2, because when we take the value of n as equal to 1, if we take the value of n as equal to 2, we will be having 2 square, which is 4 into 2, which is equal to 8 elements, in 8 electrons in the second shell. Again, in the case of the third shell, it will be 3 square, which is equal to 9 into 2, which is equal to 18. Next, after which we will be having the fourth shell, wherein we will be having 4 square, which is equal to 16 into 2, which will be equal to 32 elements. In the case of the fifth period, we will be having 5 square, which is equal to 25 into 2, which is equal to 50 elements or 50 electrons. In the case of the sixth shell, we will be again having the shell. We will be having total number of electron as equal to, in the case of sixth, it will be 6 square, which is equal to 32 in 36 into 2, which is equal to 72 number of electrons, which will be present in the sixth. Maximum capacity of the sixth shell of an atom is equal to 72 electrons. Again, in the case of the seventh shell, we know 7 square is equal to 49. So here 49 into 2 will be equal to 98. So we will be having total number of 98 electrons, which is present in the seventh shell. The question that you might ask is, sir, initially we have the total number of electrons which are possible in each shell equal to the total number of elements in that particular period. So in the later part, why is the difference? The answer is that in the case of it, actually I was going to say simply, but this is not that simple. You need to concentrate a little bit. So in the case of the first shell, we basically have only the subshells, which is S subshell. In the case of second shell, we have S subshell and P subshell. In the case of the third shell, we have S subshell, P subshell and D subshell. So therefore, my dear friends, as you can see here, in the case of the third shell, it will be having 3 different type of subshell, that is SPD. In the case of the fourth shell, it will be having 4 different types of shell, that is S, P, D and F. In the case of the fifth shell, we will be having again 5 different types of subshell, that is S, P, D, F and G. And after that, we will be having 6 different types of subshell, that is S, P, D, F, G and H, and so on and so forth. So right now, let us quickly look at the total number of electrons that we have in each of the different subshells, and let's add them up. So in the case of S subshell, we know that it contains 2 electrons. So I am writing down 2 wherever we have S subshell. In a similar way, if in case we have P subshell, we know that it contains 6 electrons. So let's write down 6 wherever we have P subshell, right? So here we have 6, here also we have 6. So when we are talking about the D subshell, we have total number of electrons which is equal to 10, right? Next, when we are talking about F subshell, we are talking about total number of electrons which is equal to 14. When we are talking about the G subshell, again, right now we will not be going into that much amount of details into the different subshells. Because G subshell will not be actually be applicable in your specific syllabus because you have only till F in your syllabus. So just for your knowledge, here in the case of G subshell, we have total number of electrons which will be equal to 18, because after 32 we require 18 more electrons to get to 50, right? So again, in the case of here G, we have total number of electrons equal to 18. And if in case we want to find out the total number of electrons, here in the case of H subshell, we just need to subtract 22, means 50 from 72 minus 50, we will be getting the value of capacity of H subshell. So as you can see, my dear friends, in the case of the third shell, we have a situation wherein we have the total number of elements as equal to 8, wherein here in the case of the third shell, the maximum number of electrons that can be added is equal to 18. This is because in the case of the third shell, we have D subshell also. However, the D subshell is actually put into the fourth period of the periodic table, and that is the reason why we have total 8 elements from the third period of the periodic table plus the 10 elements from the D subshell or the D block of the fourth period, and that is the reason why we have got here the value of 8 instead of the value of 18. In a similar way, when we are talking about the fourth type of subshell, here we have in the case of fourth subshell, we have total fourth period, we have total 4 subshells, that is S, P, D and F, wherein we have 18 number of elements in the fourth period. However, we need to add the 4F electrons. So wherein we have total 14 4F electrons in the fourth shell. So combining the total number of electrons in the fourth period as well as in 4F subshell, we get a value of total equal to 32. So this is how, my dear friends, you need to correlate the different values. Again, in the case of the fifth period, we have total number of elements as equal to 18. But in addition to that, we need to add the 14 elements or the 14 numbers of electrons to this 18. So with that, we get the value of 32. However, there is also a G subshell which is involved here, but we do not have a separate position for a G block in the periodic table because those many number of elements have not yet been discovered. And that is the reason why, because we do not have the G block, that is the reason why from this fifth period onwards, it is not possible with the help of a normal periodic table to show how we get total number of elements equal to 50. Forget about the 6th and 7th period, right? So I hope so, my dear friends, that you have now understood the total, how to find out the total number of elements in each period of the periodic table and the correlation between the total number of elements in each period of the periodic table and the total maximum number of electrons which can be accumulated in each shell of the periodic table. So initially, as we can see, there is correspondence between both of them, and after that there is a clear break, and I have explained to you in detail what is the reason for such a break.